designer's structure. Okay, yeah. Okay, let's take a look. Let's talk about this steel cable. A steel cable, a thin steel cable. Okay, about 1 millimeter. Steel cable about 1 millimeter thick diameter. Okay, so if I were to ask you to break it, okay, using your two finger, right? Okay, using your hand, not plier, everything, your hand, plier, what would you do? Okay, what is the chances that you, with one twist, can break it? Can any one of you, a 1 millimeter thick steel wire, okay, can any one of you think you can break a steel wire of 1 millimeter, okay, by using a single force? Okay, a single force, it means that, wait, maybe should open this one. Can you all see me or not? Can you all see me?
Can that can.
Yes,
Yeah,
can Betul.
okay. So we're talking about this cable. Okay, we're talking about this cable. Okay, this cable. Okay, you can see this cable. Okay, this actually quite thick, about 2 millimeter. Okay, if it's steel wire, okay, if I ask you to break it, can you just like this, can you just like this, break it like this, break it like this, using a single force, static force? Okay, if you apply like this, it will be static force. Regardless of how strong you are, you will not succeed in breaking that wire or that cable, whatever you want to call it. Okay, so it is so strong that there is no way you, a human being, can break it. Okay, it is non-logical. Okay, unless of course you are somebody very very strong. Okay, not normal human being lah. Okay, so if you are a normal human being like me, okay, 1 millimeter steel wire, there's no way you can use your static force. Okay, static force, using your strength to break it. So you cannot either pull it or twist it, whatever. You cannot break it. Okay, why? Because the steel is so strong. Okay, let me remind you that steel is about 7 times harder, stronger than bones. Okay, 7 times stronger than bone, and your bone is many many times stronger than your flesh. So what is the chances of you breaking the steel wire? Zero. Okay, but if I were to ask you when you are outside to break that wire, what will you do? You will do this, right? You will do this, and incredibly, you can break it after that. After many times, you can break it. So why is it that now? Why is it that now you can break it? Okay, when you do like this, you can break it, right? You can break that steel wire. So why is it? Is it because when you do like this, you become stronger and stronger and stronger? Eventually, you become stronger than the steel wire, and you can break it. Is that the reason? Okay, is that the reason? By doing this, become stronger, and eventually you become stronger than the steel wire. So it is definitely not. You know the answer is of course not. Okay, of course not. When you exercise, you get stronger, but only a marginally stronger. Okay, but when you do like this, you can break it. So if you do not get stronger, that can only mean one thing, and that is the wire is getting weaker. So can you imagine that because of this, which is actually fatigue force, okay, fatigue force, the wire becomes so weak that even you can overcome it. You can break it. Understand? So what is the thing? Fatigue. So that is so risky if you do not take fatigue into consideration. Because why? No matter how strong the structure, if there is fatigue and you do not take it into consideration, just like this wire, okay, after some time, people think cannot break, it will break. Okay, so that is fatigue. Okay? So fatigue means that you apply it again and again and again and again, okay, many times, okay, until it breaks. How many times? Depend. How many times? Depend. Okay. Okay, so let's go back to this lecture. Okay, so bicycle chassis, of course, has been designed to be so strong it will not fail due to fatigue failure. To fatigue stress cannot make it fail because why? We do the calculation. Who do calculation? Engineer like you all. Okay, you do the calculation and you make sure it won't fail. Okay, so that is why you are learning this. Huh? Okay, there's some more. Okay, there are a lot of fatigue stress in this shaft. Okay, in this one, on this shaft. Okay, okay, there are a lot. Okay, in this shaft, this shaft. Okay, of course, there's also a lot here. Okay, a lot. Okay, why? Because the force is repeating. Okay, so because of that, there is a lot of stresses here, fatigue stresses. And then take a look at this one. Okay, now what you see here is a fluctuating. What you see is a fluctuating axial force due to cam profile. Okay, I think you are familiar with this. Okay, so what happened is that when this thing rotate, when this rotate, okay, when this thing rotate, okay, it will push up and down. Okay, and because there's a spring, then this thing will go down. Okay, whenever it is downward, it will move down and then it will move up. Okay, what happened here is that there will be a repeating axial stress acting on this shaft. Okay, so there will be repeating axial stress on this shaft. Okay, now what about this one? This one is also the same like the first one, but the stress is due to bending. Okay, which is very more dangerous. I say that. Okay, when stress is evil, I say that in design. Okay, so this is bending, so it will bend like this, and then it becomes straight again, and then it will bend again, straight again. So that's how it happened. Okay, because of this force. This force create bending stress, and the bending stress is repeating. Okay, similar for this one. Here, there will be also bending stress. Okay, so when it is repeating, then you are talking about fatigue. And when you know there is fatigue, you have to be very careful. Okay, so this is a failure due to fatigue. Okay, now most people have designed, calculate everything nicely, but sometimes there are still unknown forces that can create fatigue force. Okay, fatigue stress and cause this to fail. Okay, similarly, this is the result of fatigue stress. Okay. Okay, so let's go to our topic today, chapter objective to analyze fatigue load and stresses acting on critical structure, to evaluate the safety structure of structure using various fatigue failure criterions. Okay, now the outline will be fundamental and fatigue strength, and then will be fatigue load and stresses. Okay, stress concentration, and then will be fatigue failure. Okay, now the first one will be fatigue fundamental and fatigue strength. We are going to look on how to determine the strength of the steel with regard to fatigue. In other words, fatigue strength. Okay, you know that we have SUT, that is the ultimate tensile strength. You have SY, yield strength. These are all static. Okay, for static stress, for static load that you have studied in the previous topic. Okay, but right now you are doing fatigue stress, so you must find the fatigue strength. Okay, now fatigue strength is provided in a lot of manuals. Okay, including the BS, NC, and so on. Okay, there's a lot of it. Okay, but what you got to learn is how to determine. Okay, how to determine that strength. Okay, so the first thing is that you're going to find out how to determine the strength, which is not straightforward as in static topic, static failure topic. Okay, a bit more difficult. Okay, And then after you are done the strength, again, you will find the load and stresses. This is the same as the previous topic. Find strength, find stress, and then, okay, in this what fatigue failure, there is something we call stress concentration. Okay, this is stress concentration. Okay, now, is there stress concentration in static loading? Yes, but it is so what you call it negligible. That's why you do not do any stress concentration when you are doing what is solid mechanic. Okay, so for our case, stress concentration is so what we call it important. Okay, because it can create extra stresses that cause failure. Okay, you're going to find out soon. Okay, how stress concentration increase the stress by not 1.5, 2 or more. Okay, so so stress concentration, and then after you have find out all the strength, you have determined all the stress. Then what you do is you make comparison. So in the topic before, we call it static failure criterion, correct? So you have DET, which is distortion energy theory. Okay, so that is a failure criterion. So fatigue case also, there is a fatigue failure criterion. Okay, there is a fatigue failure criterion. So what you do if with this fatigue failure criterion is that you make comparison between strength and the stresses. Okay, stresses will include the stress concentration. Okay, so let's go to the next topic. This one. Okay, now how does this one started? Okay, this one start by actually so many scientists has tried to uh, study, okay, about fatigue failure. Okay, and many are good work, but one that is most popular and most referred to would be this man R. Moore. Okay, it's R. Moore. Okay, okay. He create this experiment to determine the fatigue strength of material. Okay, so let me introduce to you that, okay, this is the machine. This is the machine. Okay, now what you have here, this one, this is a bearing. Okay, this is a bearing here. This is bearing. Okay, and then you have a motor here. You have a motor. Okay, you have a motor here. Okay, this is motor here. And then here you have a counter. Counter, you know what is a counter? It counts the number of revolution. Okay, the counter there. Okay, and then you have this one. This is the load. He will apply load F. Okay, why? Because this this is the specimen that this specimen. Yeah, is this one? Is this one? Okay, this is one. Okay. Okay, so this one. So what happens is that he is going to conduct experiment with creating bending stress here. Okay, there will be bending stress here. And because of that bending stress, this PEC structure will fail, will break. Okay, of course, he create thousand of this one, not one, thousand of this one. Okay, and the rule is that according to his experiment, all these specimens are totally identical. Everything, the smoothness, it is very smooth. Okay, and the shape, everything are all exactly the same. Okay, so what he did is that he will place it inside here like this, You see, it placed inside here like this. Okay, and then he will apply the load F. Okay, now the question is, of course, some of you may ask, okay, why don't just put this thing here, right? Why don't put this thing here? Why you need this thing? Why you need this thing? So complicated, right? Why just don't put this part here up to here? Okay, okay. Anyone can guess what is the answer? Why does he have to create such a very complicated structure, this one? Okay, to determine the bending stress. Okay, remember I mentioned that when there is a bending stress, there is also another stress. What is it? Transverse shear stress. So if he were to put this one just like this, okay, then other than bending stress, there will be also transverse shear stress. So what he will get will be a value that has to be calculated more complicated. Okay, so by doing this one, by doing this structure, right, this structure, okay, the bending stress will be pure bending stress. Okay, there is no transverse shear stress, and so the experiment is very, very accurate. Okay, so how does he start this experiment? The first thing he did was, of course, to determine the strength, the ultimate SUT of the material. Okay, now the material concern is what is, I can't remember, it basically is a carbon steel. Can't remember what kind of carbon steel. Okay, and the moment stress, this one is the SUT. This is the SUT of the strength, 125 kpsi. Okay, have I told you what is kpsi? Do you know what is kpsi? Come on, you all. Do you know what is kpsi? No. Now, for this SI system, we have Pascal and megapascal. Correct? You have MPa, right? Or PA. Okay, that's for stress. Okay, so that is for stress. In the imperial system, this is used, then it will be KPSI. Okay, and now they want to make it even shorter because humans tend to be lazy. They use KSI. Okay, KSI. Okay, so the KPSI and KSI is the imperial system. Okay, we have two: metric system, imperial system. Imperial system is currently being used by the United States. Okay, still used in the United States. Okay, the metric is used in Europe. Okay, and we follow your Europe system. We are using metrics, so that's why you have meter. Okay, you don't use inches. We use millimeter. The imperial use inches. Okay, they use feet. They use yard. Okay, we use millimeter, use meter, we use centimeter, right? Okay, so this one, 125 kpsi SUT is 125 kpsi is the ultimate tensile strength of this material. Okay, based on this one, based on this calculation, as you can see. So for that to happen, the force here have to be 166. Okay, force is 166. So by applying a force, pound force of 166, okay, then we have this one. So when we apply the first one, so 166. Okay, I'm writing it here. 166. Okay. Okay. So after placing the load 166, the motor was started. They switch on the motor. Right, the motor start to rotate. When the motor rotate, the shaft also rotate. Remember, when this motor rotate, the shaft also rotate. This shaft also rotate. This shaft also rotate. Okay, and the counter calculate the number of cycles. Okay, one cycle, two cycle. Okay, so when F is 166, before the first cycle is completed, okay, before the first cycle is completed, this one break. Okay, so Here we write 166 0 cycle. Okay. After that, of course, he did a few experiments, not one time, many times. Okay. Eventually, they basically they are still zero cycle break, zero cycle break. Okay, zero cycle they break. And then what happened is that after this, he plays it. I'm not sure what is the value. Let's say 150. Okay, now it's 150. Put a new specimen. After you put the new specimen, motor on. Okay, motor on, and then start counting. Okay, this time it does not break at the first cycle. It break after, let's say, I'm just assuming and give you some idea, 20 cycles. Okay, 20 cycle. Whatever after that, he used 130. Okay, we use 130, new specimen. Okay, restart the motor, and this time 100 cycle. Okay, 100 cycle. See, okay. So he continue like this, 101, what is it? 115. Okay, 115. Okay, try again. This time maybe 1,000. Okay, 100, maybe 10,000. Okay, okay. And so he continue this one. Okay, he continue reducing this one. Okay, so until it reached about 50 kpsi. Okay, continue until 50 kpsi. Okay, when he apply 50 kpsi, the structure did not break at all. Okay, the structure did not break at all. It stay strong infinitely. Okay, in other words, if the load is only 50, this shaft will never break forever. Basically, it's just continue. Okay, it is capable of handling that 50 kpsi. Okay, so he try lower, also the same. Try 40, also the same. Last forever. Okay, it does not break. Okay, it does not break. So with this data, what Moore did were to create a graph. This graph. Okay, he create this graph based on the data experiment that he got, and as you can see, it create a special line. Okay, you see this one, and then you see this, and one more here, and here you see this one. Okay, so this is the one from SUT. Okay, for SUT, we say at the first cycle. Okay, 1001, this one at the first cycle, it is at SUT. When the load is reduced, right? When the load is reduced, okay, it lasts longer. Correct. When the load is reduced some more, it lasts even more. Okay. When the load is reduced some more, F reduced some more, you get this one. Okay. And then eventually at 50, remember at F equal to 50, it comes to this one. Okay, this is called the knee. Okay. After 50, this line become horizontal, and it become horizontal forever. You know what it means? It means that if you apply the F below at 50 or below, the structure will not fail. And this is a very important discovery. Correct? So this one is called the what is the what you call it? Because different book, I forgot. This different book use different term. Wait, this is the endurance limit. Okay, so this one 50 is the endurance limit. It is the okay. This is the wait, this is the right endurance limit. Okay, so this 50 is the endurance limit of this steel. So what is the endurance limit? Endurance limit means that if you were to apply a stress lower than the endurance limit of the material, then that material will never fail. It will continue and continue and continue forever. Okay? And this is a very significant find. Why? Because if you look at here, if you look at this one, at 1006 cycle, right? Okay. Now, if you say for 1006, so if you to apply a load at here, you apply a load at here, will it fail? Can it fail? Yes, it can fail. But anything from here to here, okay, let me clear that one first. Can I use this one? Good. I'm using Foxit. Okay. Okay. So everything from here to here can fail. So if you apply the load from this one here, from here to here, the structure can fail. So if you want the structure to not fail, okay, then you must apply the load that is 50 or lower. Okay. Now, if you look from this one, you will notice that this one is 1 million cycle. Okay. So the steel, okay, after 1 million cycle, okay, after 1 million cycle, okay, if you use anything, okay, if you use higher than 51, yeah, let's say use 51 kpsi, okay, kpsi, then it will not be 1 million cycle. It will be maybe 999. Okay, still will fail. Okay, so before I proceed further into this, okay, I hope you okay. Let me explain to you now. This one here is called low cycle. That is from 0 to 10 power 3. So from 1 from 1 what is this? 1 to 1000, okay, 1000 is called low cycle low cycle life force. Okay. Low cycle okay. From 1000 to forever, it calls it as high cycle. Okay, this one is high cycle, this is low cycle. Okay, now bear in mind that later when you are drawing this one, this is called the SN diagram. This is called the SN diagram. Okay, when you are drawing the SN diagram, most of the time we will start from here. We will start from here, from 1000 cycle, from 1000 cycle. Okay, 1000 cycle. Below 1000 cycle, normally we do not do any analysis. Okay, Our analysis always start from 1,000 cycle to 1 million cycle. Okay, understand? So we are all interested in high cycle only. We are not interested in low cycle. Later you'll find this out. Okay. Now there is one more thing that you must see, that this one is finite life. What does finite life mean? Means that it can die. What does infinite life mean? That it will last forever. Okay. So here you can see this finite life. Okay. The thing will perish eventually. This is will stay forever. Okay. However, if you can see here, there is a ambiguity here. Okay, and this ambiguity is by the research. So we are, for the sake of education, uh, we have simplified this diagram to become like this. So this will be the diagram that you will be using. Okay, you're going to use this diagram. Okay, this is the endurance limit cycle, endurance fatigue strength against number of cycle of more steel specimen for the SN diagram, endurance limit. Okay, SN. Okay, SN is endurance limit. Okay, start at 1 million cycle. Okay, start 1 million cycle. This means that for steel specimen, if it can last 1 million cycle, okay, if a steel specimen can last 1 million cycle, we know that it can last forever. Okay, so if you doing your experiment, you discover that it can last 1 million cycle, you do not have to test for 2 million, for 3 million, or 4 million, 5 million. No need to test anymore. Once it reach 1 million, means that it will last forever. Okay, of course, there are external factor that can still make it to fail, corrosion, all these things, right? Corrosion can make it fail. Okay, assuming there's no corrosion, everything is fine. Okay, once you have discovered that specimen can last 1 million cycle, means that it will last 2 million cycle, 10 million cycle, Google cycle. Okay, Google cycle, you know, right? A Google cycle is uh, a value with 100 zero. Okay, okay, like 1000 have 30. Google is 100 zero. Okay, so it can last forever. Okay, but if it's less than 1 million, then it will fail sometime. Okay, it is less than 1 million cycle. Okay, it will fail sometime. Okay, now take note that this one is only true for steel. Why is it so stubborn? For steel and titanium. Okay, this one, the fatigue strength, or we call it the endurance limit, only exists for steel and titanium only. Aluminium do not have endurance limit. Okay, what happened when you use aluminium? It will continue to go down. Okay, so those of you who want to create something that lasts forever, you cannot use aluminium. That's why if you see in the Grand Prix, right, they use aluminium. Okay, they use aluminium because after the race, they throw away the old engine and replace a new one. Okay, your car, can you afford to do that? Okay, today you drive your car, after you go home, change the engine. Okay, that one is miracle lah for you all lah. Okay, so for aluminium, it will continue to go down. The only one that have endurance limit will be steel and titanium. Okay, take note. Remember, this is very important. Okay, so far, any questions? So what is the significance of SN diagram? It will give you give you the fatigue strength of the material. Okay, you determine the fatigue strength of the material using the SN diagram. Okay, you will use the SN diagram and all the equation inside it, okay, to determine the fatigue strength of the material. Okay, once you have the fatigue strength of the material, then you can start calculating the stresses. After you have calculated the stress, you can calculate the stress concentration factor, okay, to give you total stress. And then you make comparison using the fatigue failure criterion. Okay, any questions so far? Okay, okay. So this is to calculate strength. Okay, so this is what I mentioned just now. Okay, I mentioned just now that we focus for high cycle only. Now what you see here is start here from 1000. Okay, so when you draw your SN diagram, most of the time it will be like this. Okay, now the SN diagram here, if you can see here, yeah, this is the some called S10-3. I prefer to call it S3. Easier. Okay, S3 equal to 0.9 SU. What is SU? SU is SUT. Okay, SU is SUT. So this one, the brown color, okay, is the endurance limit of most specimen, okay, under bending stress only. Okay, so if the specimen is under bending stress only, then you will develop your SN diagram based on this brown line. So your SN diagram will be 0.9 SU. You have to find out what is the SUT of the material, and then you'll be here. Remember, this is 1000. So you'll be here 0.9 SUT, and then you have to find 0.5 SU. Okay, SUT, and then you draw this line. Okay, and then of course this one is horizontal. Because why? Endurance limit. Okay, that one if it's bending stress only. Okay, now what happens if it is axial only? Axial only. Okay, like just now I show you the cam. What is axial only? Then it is the blue line. So the blue line, the SN diagram will start from S3 S3 is equal to 0.75 SU to 0.45 SU. Okay, I don't want to talk about SN prime yet. Don't want to talk about SN prime. Okay, SN is equal to 0.45 SU. That is for axial. No eccentricity. What does no eccentricity? In other words, the axial force is fully at the center. No offset. Okay, if it's offset, then it becomes buckling. Okay, so it's not axial stress anymore. Okay, it falls under buckling. Okay, so if there is no eccentricity here, and it's a torsion, then you see this one torsion, S3 is equal to 0.72 SU, and then this one SN is 0.29 SU. Okay, so when you are doing your analysis, you have to determine what kind of loading, what kind of stress. For example, the experiment just now, right? It is bending, correct? Not? It is bending, right? Because it's bending, you are going to draw the brown line. Okay. If it is only twisting, then you will use the green line. If it is axial, then you will use the blue line. Okay. Now, question that you will ask me later if I don't tell you answer now. So, what happens if it's a complex loading, complex stress? What happens if it has bending, if it has axial, it has torsion? What do we do? Okay, take note. If it's a complex case, then it automatically fall under bending only. Okay. In complex case, complex loading, you will assume this one, the brown line. Okay. If there's a forget about the green line and the blue line. Okay. If it's a complex stress case, you will use the brown line. Okay. So it's not so difficult. So by this, you will have calculated, okay, you can calculate the strength of the material. Okay, the strength material, I mean the fatigue strength of the material. Okay, remember, this one is endurance limit. This is the fatigue strength endurance limit. Okay, it's horizontal, horizontal, horizontal. Okay, now let's talk about this Sn prime. Now, Sn prime refer to more specimen this endurance limit. Okay. Now, Sn prime refer to more endurance limit. This one. Okay. The endurance limit of this specimen, like this, absolutely smooth. This kind of loading, correct? Okay, for this kind of experiment, then the Sn, the endurance limit that they got will be Sn prime. Okay, so Sn prime here will be more endurance limit, more specimen endurance limit. So what is Sn here? Now Sn here is your specimen. Okay, your specimen. Okay, don't get confused. It's not so confusing. Later you find that it's so easy to understand. Okay, your specimen, because why? When you do your shaft, when you create your shaft to rotate, okay, you will not create something exactly like more specimen. More specimen is perfectly smooth. Okay, when you do your experiment, how many of you can produce perfectly smooth shaft? Yours probably means machine using lathe machine. Okay, because of that, your Sn, okay, your Sn is of different value compared to more specimen. Okay, understand that? Okay, so that's the difference. So Sn prime refer to more specimen endurance limit. Sn without the prime is your experiment. Okay, is your specimen. Okay, okay. So if it's okay, we'll continue some more. This is the equation that you are going to use to determine the strength of the material. Okay. Now here you have Sn is equal to S dash N Cl Cg Cs Ct Cr. Okay. So like I said just now, your specimen is not the same as the one by Moore. Okay. Your temperature is not the same as the temperature of that Moore specimen. Okay, for example, maybe you're creating a shaft for your motorcycle. Okay, for your crankshaft for your motorcycle, you know that your crankshaft will be very warm. Well, in fact, will be very hot. Okay, the temperature will probably reach around 80 to 90 degrees. Because of that, okay, the strength of the fatigue strength will be lower. Okay, so that one will fall under Ct. Okay, this is the temperature constant. So what is this? We call it the fatigue strength factor. Okay, so fatigue strength factor for temperature is Ct. Okay, so if the temperature is warmer, then you have to find Ct. It's just a matter of reference. Okay, so take a look at here. You have Cl. Cl is a load factor. Okay, Cl is a load factor. So first you have bending. Okay, you have axial, you have torsion. Okay, according to your experiment, okay, is the load bending, is the load axial or torsion? Okay, if it is bending, then Cl is equal to 1. If it's axial, Cl also equal to 1. If it's torsion, CL is equal to 0.58. Okay. Now torsion means pure torsion. Axial means pure axial. Okay. Now what happens if there is bending, there is axial, or there is bending and torsion? Then you will use bending. Okay, remember? For complex case, refer to bending only. Okay. Understand? Now CG. Now CG, if it's 0.4, that is 10 millimeter. Okay. Anything less than 10 millimeter, this is the value. So for bending, 1.0. For axial, 0.7 to 0.9. I think you better use 0.8. Okay, we're going to use 0.8. Okay, we're gonna, otherwise it will be quite complicated later, right? When I mark the paper. Okay, a distortion is 1.0, right? Now, if the shaft is larger than 10 millimeter, then it fall under this category. Okay, well, so the what CG is 0.9, CG also 0.8. Okay, and CG, the CG for torsion is 0.9. Okay, right? So what happen, you have bending and axial and torsion, then use this one. Okay, if it's complex, use bending. Surface factor. Now, surface factor refer to this how you what is the finishing of your specimen. For example, if you look at this one, you can see from here this is mirror smooth. This one is mirror smooth. Okay. Your specimen most probably will not be mirror smooth. Okay. So to this one, you must look at figure 813. Okay, 813 is given here. This one. Okay, this 813 is given here. Okay, for your information, the slide. Okay, the PDF for this one is already given in the portal, right? It's in the portal. So if you want to see a clearer diagram, then you can download them. Okay. Okay. So, okay. So based on this, the factor for CS is surface finish factor. Okay, surface finish factor. Okay, we'll take a look at this one. Tensile strength. Okay, in case KSI, remember KPSI is equal to KSI. Sometimes they use KPSI, sometimes they use KSI. Okay, don't get confused. Or if you want, you can use GPA. Okay, GPA is 1000 megapascal. Okay, so you can refer this one. So all you have to do is determine what is the SUT of the material. Look here, look underneath here, and then go up. Let's say it's 140 KSI. 140 KSI, go up here. What is the material? Okay, for most specimen, the material goes straight up into here. This is most specimen. So what is the value of the surface finish factor? Okay, the surface finish factor is 1.0. So it's horizontal, basically horizontal. This line is horizontal for most specimen only. Okay, now yours will never be this good. Yeah, yours will, if you can get fine ground is already good enough. Most of the time yours will be machine or cold drawn. Okay, now what's the difference between machine and cold drawn? Okay, machine, wait, what's the difference between machine and fine ground? Okay, now fine grinding. Okay, fine ground means it's grinded. Now grind do not cut, they actually they rub, they use friction, okay, to clear the surface. That's why it's very smooth. They do not cut. Okay, different from machining. Machining, they have a sharp object which cut into the material. Okay, so anything that cut into the material is called machining. For example, lathe machine, it cut, so it is a machining. Okay, so if the finishing is by lathe machine only, then you must use this graph. You must use machine graph. You must use this one. Okay, so what happens if you do milling? Milling is also cutting. Okay, so it's machining. What about shaving machine? The same. Okay, everything that got to do with cutting. Okay, now there is a sharp object to cut, then you fall under the category of machining. Okay, only special people. Okay, so if project, then you will use this one, fine ground. This one is only special project. Okay, for most of the time in your experiment, it will be machine or cool drawn. Okay, what about hot roll? Okay, now hot roll means that this is what I say. When you buy this shaft, you find the shaft. Okay, buy the shaft. Okay, remember I mentioned to you that you can buy the shaft. It can be a nail. It can be what I can't remember. A nail. That's right. So basically, right, all these are hot roll. Okay, they are hot roll. Why? Because they are melted and then they are rolled out of the fabrication machine lah. Okay, hot roll. Okay, so of course hot roll have anneal, has what the other two I can't remember. Okay, now hot roll means that it is produced by hot rolling lah. Okay, so the thing become hot and then when it's hot, okay, and it's soft, then they pull it out, okay, or they squeeze it out of the hole lah. Okay, now cold drawn means of course it is quite cold, so it is quite cold, right? Quite cold, so it was forced, so a lot of pressure is required, and because it's quite cold, the expansion or compression is very small. Okay, because the compression is small, that's why the surface is quite smooth. Okay, the surface is quite smooth, that is comparable to machine. Whereas for hot roll, because it's hot, when by the time it cool down, the surface become quite rough. Okay, quite rough. Okay, then worse than hot roll will be forging or casting. Okay, you have this one, forging or casting. It is casted or forging, then you take that one. Okay. And then corroded in tap water, that one is beyond our scope. Okay, so this is a diagram A13 that you must be familiar. Okay, this is to get the surface factor CS. Okay, now CT, if the temperature is less than 840 degrees Fahrenheit, now 840 degrees Fahrenheit is how many? 840 degree Fahrenheit is equivalent to 448, okay, Celsius. Okay, it's 448 or 450 lah. Okay, 450 Celsius. Okay, so is anything less than 450 centigrade, then if it's less, then bending will be 1.0, axial 1.0, torsion 1.0. Okay, it is between 840 and 1020. Okay, then is this one. Use this one. Okay, now what is the significant value of this one? 1020. Okay, at 1020 degrees Fahrenheit, okay, the steel, okay, the steel start to weaken. Okay, not melt. Melting is 1020 is what? 1020 is about 620 degrees centigrade. Okay, this one is 620 degree, round lah, 630 lah, centigrade. Okay, centigrade. Okay, at 630 degrees centigrade, steel will start to weaken, not to melt. Steel melt at 1200 degrees centigrade. Okay, steel will melt at 1200. At 630, it does not melt, but it start to weaken. Say, no need to talk about fatigue stress. Okay, if it's higher than 630, okay, the loading, okay, the structure will fail by itself. Because why? It's getting weaker and weaker and weaker. Okay, so it cannot be higher than 630. Okay, so that's significant of 630 or 1020 degrees Fahrenheit. Then if this is the case, then use this one. Okay, finally the CR, reliability factor. Okay, now if reliability factor 50% reliability 1.0, 90% 897, 95% 0.868, 99% 0.814, 99.9% 0.753. Okay, now this one where engineer will decide. Of course, the experienced engineer will decide what kind of what kind of reliability you want. Okay, now you'll find later that a lot of other stuff, bearing, gear, they have their own reliability. So if you were to use for this one, let's say 90 degrees reliability, for your bearing 99, for your gear 95, then actually it's not quite wise. Okay, the best is they all to be about the same reliability. So when they fail together easier. Okay, so reliability based on this one, normally it will be given. If it's not given, then assume this value CR equal to 1. Okay, if reliability is not given, CR is equal to 1. If temperature is not given, CT is equal to 1. Okay, boleh? Okay, CR and CT equal to 1 if it's not given, because a lot of question doesn't say anything about reliability or CT. So you will assume CT, CR equal to 1. Okay. Okay, so the endurance limit Sn is for pure load case only. For complex loading, refer to table 8.2, page 27. We'll go there later. Okay, so now that you have gone to here, I want you to look at this problem. Yes, one. Okay, I want to give you 15 minutes. Okay, I want to give you 15 minutes to find out what will be the Sn, the endurance limit of this. Okay, now what is this? This is a round shaft made of IC 1050S roll. Okay, is part of a powered machine. Okay, during application at temperature 250 degrees centigrade, a tensile load of force from 10 Newton to 500 Newton and a twisting force of 5 Newton meter to 14 are expected. Reliability of 99% is needed. So what happened? This is a powered machine. Okay, to nail this this rivet. Okay, not with nail rivet. This is a nail to twist and press a nail, or screw, not nail, screw. Okay, so you use one to twist the screw, and when you twist the screw, you must also force axial force. Okay, you press it inside. So that's why. So there is two force here. Okay, so this is basically a screwdriver, something like a screwdriver. Okay, so a tensile load force of 10 kilonewton to 500 Newton. Okay, so the load is varying from 10 to 500 Newton. So this one is not important to you. Is the value of this one. What you need to know is that it is a tensile load, and tensile load is axial. Okay, axial load. Okay, so the load here, one of the load here is axial. Second one is a twisting force. So that's a top here, 5 to 14 Newton meter. So there are two forces here. Okay, so you have a tensile or the axial stress, and you have also twisting stress that is a top. Okay, so what I want you to do is, what I want you to do now is using what you have learned here from this one. Okay, I want you to calculate your Sn for this one. I want you to calculate Sn. Okay, I want you to calculate Sn. Okay, for this part. Yeah. Okay. So the question here is calculate the endurance limit. Okay. So it's now the ball is in your court. Try to find out. Okay. Do take a piece of paper. Okay. If you're using tablet, that's even better. All right. First of all, what you need to know to do is to find this one. You need to find this one. You need to find the SUT of the material. Okay. You need to find the SUT of the material. After you find the SUT of the material, then you find this one. Okay. Okay. So this one S and dash is equal to 0.5 SUT. Okay. So you need to find this one first. Okay. Now, so take out your piece of paper. Okay. And then open up your manual or your PDF file and look for the strength of this material. The material is IC1050. Okay. I assume that all of you has already got it. Okay. If you haven't, that means you are sleeping. And please tell me what's the answer for SN. Give first. I want to know what is the endurance limit of this screwdriver type. That question can be obtained from the portal. Okay, 1050 Astral, the tensile strength is 723. The yield strength is 413.7. So that's the value. Okay, use that. Okay. First of all, SUT. So first of all, S comment cancel SUT is equal to SUT 1050 Astral is 723.9. SY is equal to, you become habit and always find SY also. 413.7. Right? Okay. So what you need now is to find out Sn. Okay. So you know that Sn prime is equal to 0.5 SUT. So it will be equal to 0.5 times 723.9. Okay. So basically it will be about 362, I think. 362 MPa. Correct. Okay. And then What about S3? No, S3. Oh, S3 is equal to S3 is equal to, how do I do this? Wait. Yeah, yeah, yeah. S3 is equal to 0.9 SUT, this one. Yeah, which is for bending. Why is it we use one for bending? Why do you use the one for bending? Because it is complex load. Okay, there are complex stresses. There are two stresses. So that's why we use the brown line. Okay, use the brown line. So S3 equal to 0.9 SUT. Any problem? Anyone has any question? So we go to 0. S3 equal to 0. Uh, 0. Why is this so thick? 0.9 SUT. So will be equal to 652 roughly MPa. All right. Okay. So what is this? This is Mohr specimen. Mohr specimen. Okay. So what you need to do is to find your specimen Sn is equal to Sn dash time. Okay. Time what? Look into this one. Okay. You have here Sn CL, CG, CS, CT, CR. Okay, you remember? I can. Okay, CL, CG, CL, CG, CS. CL, CG, CS, CT, CR. Where is the zero? C, 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 CL, CT, CS, correct? C, CLCG, CLCG, CS, CT, CR. Okay? Right? So what you need to know is find out what is CL. Okay? Let's go and find out what's the value of CL. Okay? Now take a look at this one. Take a look at this one. Here, CL is equal to 1.0 because why is it 1.0? Because it's complex. So we go back. So Fn is equal to 6362 times 1 times Cg. What is Cg? Where is Cg? Turbidal material. Where's my note? Where is Cg? Now Cg is, what's the size of the shaft? The size of the shaft is 12 millimeter. 12 millimeter. Okay, 12 millimeter. Okay, so it becomes 12 millimeter. So you must use this one. Wait. No. There are two parts that can break. either at 8 or at 12. Okay, CG, what's the value of CG? Do we take 0.8 or we take 1.0? Okay. If you look at the question again, the part that is most critical with this one, why not? Okay. Comment. The part that is critical will be this one. Okay. Or here. Okay. Based on your judgment, based on our judgment, we know that this one is going to break first. This one is stronger, this one is larger, right? This part is larger, it's stronger, so it will break here first. So we are using diameter 8. Okay, so diameter 8. Okay, so if we were to look at the fatigue slide here, okay, if you take fatigue slide here, then you see that we have to use 1.0. Remember, cannot use this one, cannot use this one, because why? This is a complex case. Cannot use this one because it's a complex case. Okay, and because it is 8 millimeter, so we use the one at the top. We cannot use this one. Okay, so that is 1.0. So that's the value of CL. Okay, so this is 1.0 time okay, CL CGCS. Okay, no? CL CGCS. Okay, CGS. Correct. Okay, and then surface factor, look at 813. Okay, what is the material? What is the material? A round and rotating shaft made from IC 1050 is part of a powered machine. During application, tensile load force of 10 Newton. If the machine is designed for infinite life, determine the safety factor for the proposed machine. Use the modified Goodman for fatigue analysis. Okay, so we can assume this to be machine. Okay, machining. Okay, because it doesn't say grinding, so it will be machining. So machining will be, if it's machining, the what is the SUT is what's the SUT? You know? SUT is 724. So if you look at 0.7, 0.7 here, if what is this? 0.7. Okay, so 0.24 here will be here. Correct? 0.24. So if we were to go up, so if from here I were to go up, okay, machine, so you will have this one. Okay. Okay. Does it move just now? Okay, it moves. Okay, 0.724. So it should be, because this is a machine, so it will be here. Okay, so 0.7, 0.75 around there, 0.75, 0.74. Okay, so the this one is 0.0 Why is so difficult? Answer 0. 0.74. Okay, that is CS. What about CT? Is temperature given? Temperature is it given? Okay, no temperature, so time 1. And then this reliability is 0. What is reliability like? What's the question? Oh, temperature is 250 degrees. Evaporation at temperature 250 degrees. Okay, reliability of 99. Okay. Okay, 250 degrees. So if you look at the value here, okay. Okay, value of CT.
Sorry.
Huh?
We can't see the screen.
You cannot see the screen now?
No.
Huh? No. Oh, wait. Let me see first. What happened? Okay. It's okay now. I make it into a tablet mode just now. Maybe it won't allow that. Okay. Okay, never mind. So I will stick to this one. So we have so far you understand what's going on here? SN. Do you all understand so far? Were you lost just now? Come on, somebody.
Okay, Doctor.
Can okay.
Yeah.
So 360 times 1 times 0.74, that is 362, 1, CG1, CS 0.74, CT is 250 degrees, is 250, 250. So we have to look for 250. Okay, can you find out, can you calculate what is the value for CT at 250 degrees? Okay, now 250 degrees, you have to convert them into Fahrenheit. Okay, convert them into Fahrenheit, 250 degrees. 250 degrees is definitely, just now we calculated 140 is about 300 something, right? So 350 should be this one. One, correct? Because just now, what? 840. Oh, 840 is 448. 448. So less than 448. So you agree, right? CT is equal to 1 because this is 4. Because this is 448 degrees centigrade. Okay. So since temperature is 250 degrees, so we can calculate that this one is 0. 1, 1, 0.74, CT times 1, and then times CR. CR is equal to 90, what's the what? 99 degrees reliability, yeah? 99 degrees reliability. So here you have 99 degrees reliability is 0.814. So you get 0.814. What is this? Yes, okay. 0. What is going on? What is this? What is this? Hold on. I don't understand what is going on. I try eraser first. Okay, let's try comment, cancel. Okay. Yeah. But battery habis. I do not know what's going on. Okay. Okay, I do not know why that one doesn't want to write. Oh no. Zero point. Is there something I don't know? Don't tell me my computer hang or no. Hold on. Oh, the software hang. Okay, the software hang lah. Okay, man. Okay, Okay. So I will use this one. Yes. Okay. It's back, 0.74 time time 0.814. Correct. 0.814. So I calculated this one to be around 224 megapascal. Okay. So what is this? This is your specimen endurance limit. Okay. So in other words, if you want, if you want this one, if you want it to last forever, if you want them to last forever, remember, you want it to last because why? Was design good. If life, calculate means calculate endurance limit. So you want to find out. Calculate the mean of tolerance stress, determine the safety factor for the proposed design, use and modify. So what we have here is the SN diagram. So once you have this one, you basically have you have discovered or you have determined the fatigue strength of the machine. So later what you can do is you can draw the SN diagram, based on what you studied before. So it will be take this one. So based on the brown line, so SN here will be equal to this one. So S3 will be 0.9 SU. right? S3 0.8 is 652. So this one will be S3 here will be 652. And then your 1000 here will be your this one. This is 1000. This is 10 to power 6. Okay, so this is your SN 224. And so this is the line that you are required to draw. Okay, this will be your SN diagram that you are going to use later after you done the stress calculation. Okay, any questions? So it's not so difficult. Okay, any question? So basically you get 1/4 of the marks already. Remember, if you get this one wrong, everything gone. Okay. This one is not difficult. Most students should have no problem getting this one right. Okay. So I assume that you have no problem with this one. So can we proceed with our lecture some more? Any problem so far? Okay. You all are quiet. Make me nervous. Are you still there? Okay. So if you have no problem, we'll go back to our slide here. So this is the first part. Okay, first part, finding SN. Okay, finding SN is the first part. What is SN? The endurance limit. Basically, we're saying that it's the fatigue strength of that material. Okay. Okay. After you have done that, okay, you have calculated everything. So now you have to start fatigue stresses. Okay. Now, fatigue stresses is like this. Okay, when the load is repeating, so like this, repeated stress. Okay, repeated stress, then it becomes fatigue stress. Okay. Now, repeated stress in this case, okay, the term repeated stress, this subject term for repeated stress means that the load, you can see this one, here is 0, okay, here is 0 stress, okay, here is 0 stress. So you have here pressure, okay, when this one is put down, so this one will bend, so there will be a stress here, so the stress will go up to here, and then it will be released, it will be straight, and then the stress will go here, and what here? No stress, 0 stress, and then it will continue again, okay, and then will go up again here, full stress, okay, and then it will be 0 again, and this one. This is called repeated stress. Okay, so it is apply, let go, apply, let go, apply, let go. This is repeated stress. Okay, now there is another one, repeated stress, but in this subject, the term used is reverse stress. What is reverse stress? Reverse stress is like this. Here is 0 stress. So here is tensile stress. Okay, tensile stress 100, let's say, and then here 0, and then it go to 0 compressive, so I put minus 0, and then go 0 back, and then here is 100 again. Okay, sigma max, and max, and then 0, and then sigma min again. Okay, this is minus 100, and continue like this. Okay, so the mean stress is 0. For this one, the mean stress is this one. This is the mean stress. Okay, the mean stress will be sigma max divided by 2. Okay, okay. So here the mean stress is 0. So if you take a look at this diagram, when I apply the load like this, apply load here, okay, it will be sigma positive. Why is sigma positive? Because you know that by virtue of this part, okay, this part is A, okay, this part is B, okay. So by virtue of this one, now here, if you look, because of the bending, here will be compressive, here will, here will be tensile, here will be compressive, correct? Okay, this is tensile, so this one will be compressive. So the one at the top, by virtue of the force coming from the top, because the force is coming here like this, okay, the force coming like this, so here will always be compressive, here will always be tensile. So what happens is that A is rotating. Okay, A is rotating. So after a while, A will rotate, A will be here. And B, of course, will be here. At this time, okay, this part, which is A, will be at the top. And so it will be compressed. Just now it's tensile, now it's compressed. Okay, whereas B just now is compressed, now will be tensile. Okay, so that's why you get positive, then you get negative. Okay, and then what happens that this thing will rotate again. So now A will go back here, and so it will be positive again. Okay, it will be positive again, and then it will rotate some more, then it will be negative again. Okay, so this one, when the value here 100, and the value here is so 100, okay, value must be the same, then it is called reverse stress. And most machine actually suffered this kind of stress. Okay, okay, they and this they tanggung okay, they okay, they support, okay, they support this kind of most machine. Okay, piston, most specimen, the loading is like this one, reverse stress. Okay, this one is very seldom. Okay, this most side. So you look at the machine, this is the one that is most used. Okay, so the stress will be 100 maximum, and then negative maximum, and then positive maximum, negative. Okay, so we come to the end. The mean stress here will be 0. Okay, now the value between here, between the mean stress and the sigma max, okay, value here will be sigma A. What is sigma A? Sigma A is called alternating stress. Sigma A here, sigma A is alternating stress. Okay. The line at the middle, this one, is called mean stress. So here, this is the mean stress. Okay. This is the alternating stress. Okay. Oh, sorry. Oh, yeah, that's right. Okay. Oh, sorry. Here, the center. Okay. The center is a mean stress. Okay. Mean stress is always a center between sigma max and sigma min. Mean stress is always in between sigma max, which is this one. Okay. And sigma min here. Okay. Somewhere here and here. So sigma min is this one. Okay. Okay. So based on this, you can calculate what will be the sigma min. Okay. So finding the stress is about finding sigma m, which is sigma min, mean stress, and finding alternating stress. Oh, it's here. Okay, this is one, mean stress. This one, okay. As long as you find sigma m, as long as you find sigma a, you have covered 2/3 of your work. Okay, but mind you, okay, finding sigma m and sigma a is the most difficult for the student. Okay, many make mistake here. Okay, so now when you do your calculation, okay, here, okay, as you can see, for fatigue to occur, there must be what is increasing load and decreasing load, or you can say repeated load. Okay, there must be a repeated load. So here there will be a repeated load. So this one is sigma max. This one is sigma min. Okay, sigma max, sigma min. Okay, this one is sigma max. Okay, it's given here sigma max, and this one is sigma min. This one. Okay, the mean stress is at the center here. Okay, here the mean stress is this one. Okay, from mean stress to the sigma max is sigma a. Okay, from mean stress to the top here is sigma a. Okay, the sigma min from here. Okay, sigma min from 0, this value. This is sigma m. Okay, this is a mean stress. This is sigma m. Okay, so this one also from 0, this is sigma m. Okay, now how to calculate sigma A and sigma M based on sigma max and sigma min? Okay, so this is the equation. Yeah, this is the equation. Okay, this question. So use all you have to do is calculate sigma max, find the sigma max, find sigma min, you will get sigma M. Okay, now sigma max plus sigma min equal to, you get sigma one. So this is one that you need. Okay, because this is one that you are going to use inside the failure criterion. Okay, similarly, sigma A is equal to sigma max minus sigma min divided by 2. This is the equation you are going to use every time. Okay, what you have to do now will be your nemesis. Okay, nemesis is find sigma max, find sigma min. Okay, now how to find sigma max, sigma min? Use your solid mechanic. So what is the difference between your solid mechanic and or our stress analysis? Okay, stress static failure previously is that when you do fatigue failure, you have to calculate 2 times. Okay, your first solid mechanic calculation will be based on this value. The second one will be based on this value. So you will always get 2 values. So based on that, you will get sigma max. Based on that, you will get sigma max. And based on your calculation again. So in other words, when you do fatigue failure, you have to do 2 calculation of solid mechanic. Okay. So if you are finding bending, you have to find 2 value of bending stress. One of them will be maximum. One of them will be minimum. If it is axial stress, then you have to calculate 2 axial stress. One will be at maximum and one will be minimum. Okay. So it's always like that. It's not so difficult. It's just that you have to do two calculation at the same time. Okay, one will be to determine sigma max, which is the highest one, and then you have to determine the lower one, which is sigma min. Okay, now if you have sigma, is equal to 10 MPa, and you have another sigma equal to minus 500 based on your calculation. Okay, which one will you consider as maximum? Which one will you consider as minimum? Okay, now most of you will think that this one is maximum. The one thing that is wrong. Okay, the one that is more positive, is the maximum. The one is the more negative is minimum. So here 10 is maximum. So this one is sigma max. This is sigma min. Okay. So if you have here 0, is also sigma max because it's more positive than minus 500. So do not get this thing wrong. Okay. Sigma max is most, which one is most? So you cannot determine earlier which one is maximum. Okay. But after you do your calculation, it is discovered one is 0 MPa. Okay. The other one is minus 500 MPa. So the 0 is max, sigma min, minus 500 is sigma min. Okay, so take note. Okay, don't make mistake here. Okay. Any question? But for your information, I have video. Okay, I have video of this note. Okay, in the portal. So those of you who is a bit lost, you can go through the video. Okay. Now, just now is to calculate sigma m and sigma a. Okay, sigma min and sigma alternating. Okay. Now you are going to calculate stress concentration. Okay. Now for basic type of notches in stress concentration, there will be 3 of them. Actually, in engineering, there are a lot more. Okay. But for our subject here, there is 3. Groove. This is groove. This is groove. Transverse hole. This is transverse hole. This one is transverse hole. And shoulder. This is shoulder. This shoulder. This is shoulder. And this is shoulder. Okay. So when you have you need to determine your stress concentration, you must decide which one, whether it's groove, transverse hole, or shoulder. Okay. It's not so difficult. You have no problem deciding this one. Okay. After you have decided this one, then okay, after you have decided, you have to find the KF. Okay. Okay, so I'm going to show you an example. This one. Okay. Give you example. Okay. Now this one is 25 by 25. So the stress P is 150. One is a notch, means that it is straight. This one have a notch. What you see here will be what we call here as this one, groove. Okay. Now, in real life, groove can be scratches. If you scratch the surface of your specimen, that will be groove. Okay. So please take note. Do not scratch your specimen. Okay, it's very important. So now the cross sectional area of this one is AN. Here is AN. AN 625. So the tensile stress here will be 240 megapascal. Correct? This is no problem. Now, this one now, there is a notch here. Okay, there's a notch here. Okay, the notch here is 2.5, right, as you can see. So 80 here will be this one. Okay, as you know, failure will occur here. Okay, failure will occur here, this part here. Okay, because it's the smallest part. Okay, so 80 here is 25, which is 1, time 30 minus 5. 30 minus 5, 30 minus 2.5 plus 2.5. So the minus 5 here, the 80 is also 65. So you can see the area here is the same size. So by right, sigma 0 here is equal to 240, also the same. Okay, now sigma 0 here, I put sigma 0 here, means this is the value without stress concentration. Okay, so without stress concentration, the stress is also 240. Okay, so now after you consider that this one there is a groove here, so you must calculate the stress concentration. Okay, so what you have to do now is look into your table. Okay, look into your table. Where is my, where is, oh yeah. Okay, you have to look for, okay, this is figure 4.39. Okay, look for it, you'll find this value here. Okay, so now I'm going to open that part here. Okay, this one is easier. Okay, so you have here many, okay, many of this chart. So A, B, C, you have D, E, F, G. How many you have? You have a lot. Okay, you have a lot of them. Okay, so what you have to do now is to determine which one will be same as your specimen. Okay, which one is the same as your specimen? Okay, you have this one, you have this one. Okay, you have this one. This one is with transverse hole. This one with a notch. Okay, this one with shoulder. Correct? Okay, understand? So this one is just nothing. Okay, so take a look at this one. So based on our diagram just now, okay, based on this one, it can look like this. Okay, so it look like this. Okay, look like this. So if you look into this table, okay, you look into the table, this is not the one. This is the one. Okay, remember, you can see the groove here. You can see the groove here. Okay, so this one, there are two of them. So which one are you going to use? Let's be one more, right? Okay, two. Bending and tension. Okay, no twisting. Okay, so you have this one. Okay, here you can see that the value here. Okay, so we, there's the one. Okay, so I'm going to make it larger. Okay, so you can see here, this one is R divided by H. What is R? This is R. What is H? Small h. This is small h. So small h is this one. So R divided by H is 2.5 divided by 25. You get 0.1. Okay, okay. And then the next one you need will be h divided by h. Okay, it is h is this one. This is h. So this h is 30. Now h is again 25. So you have a value of h by h is equal to 1.2. Okay. So what you need, okay, what you need to do now is to determine, okay, now here h r h is 1, h divided by h is this one. Okay. So what's the value of this height? 1.2. Okay. So here you have r by h is 0.1. Wait, there are two of them. This is for, there are two of them, right? Okay. Remember just now, there are two of them. One is for bending, one is for axial. Okay. If you take the one for bending, you'll fail. Because the loading just now is axial, correct or not? The loading just now is axial. Okay, axial. So you must take the one for axial. Okay. So take note. Okay. So you have to select properly. This is for axial loading. This is for bending. Okay. So you cannot make mistake here. Okay. So now you have this value. So RH is 0.1. So you have go up here. So go up here. Okay. And then H divided H is 1.2. Now this is 1.01. This is 1.05. This is 1.15. Can you see 1.2 here? Can you see 1.2 here? Okay. So 1.2 will be around here. Okay, 1.2 will be around here. Okay. Okay. This is 1.2. So what happened is bring it to the side here. So you get the value for this one, KT is equal to 2.42. Okay, based on my diagram. Okay, but here I've done the calculation already. Okay, so KT is 2.38. Okay, so KT is 0.38 based on here. Okay, because my curve is very ugly. Yeah. Okay, so 2.8, so KT. So you get KT. Remember, you must choose the correct chart. So now you get KT. Why you need KT? Because you want to use this equation. You need KT. Yeah. Okay, you need KT here. So you need to find Q. Now Q, you look into this diagram. Figure 8.24. Okay, look into figure 8.24. You will see this one. Okay, so you have here. Okay, okay. SU is 400 megapascal. Now, as you can see here, this one is in kpsi. Okay, this one is 50 KSI or KPSI. This is 60 KPSI. Okay, this is BHN. Okay, Brinell hardness. Okay, so we are going to use the KSI. The MPa is not given here, so what you have to do is you have to convert MPa into KPSI. So you have KPSI is equal to 58 KPSI. Okay, SU 400. Okay, SU is 400 equal to 58 KPSI. R equal to 2.5 is equal to 0.1 inch. Okay, so here you look at this. R is equal to what? R equal to 1 inch. 1 inch. 0.1 inch. So R is equal to 0.1 inch here. Okay. Okay. SU is equal to 58 kpsi. Okay, 58 kpsi. Now, you have two value here. Okay, do not get confused. This one is for bending. Remember? This one is for bending. This one is for torsion. This one is for torsion. Okay, this one is for bending or also axial. So you must use this one. Okay, use the one on the left. Okay, so based on this one, you said 58 kpsi. 58 kpsi is about 60, so it will be this one. Yeah, this one. Okay, so Q will be equal to here 0.76. Okay, so Q is equal to 0.76. Okay, so once you get this value, you can put inside here. Okay, put inside here K, Q is 0.76. So you have Kf is equal to 2.05. What is this? This is the stress concentration factor. This is stress concentration factor. Okay, and so what is the stress here? Actually, what is the actual stress here? The actual stress here is equal to this one. 2.05 times sigma 0 will be 492 MPa. So although the load is the same, okay, although the load is the same here, load is the same, okay, and the size here is also the same. This one is actually larger. This one is larger, right? Okay, but because of this notch, that make it 25 also. So this one is actually 400. The load become 492. So the stress here is actually sigma T here is 492 MPa. Okay, so make your comparison. Because of this small notch, okay, the stress at this part here is actually 492. So just imagine, because of stress concentration, the value rise up by more than two times. Okay, and then remember, because of fatigue strength reaction, the strength is also reduced. So the strength is reduced, the stress is double. Can you imagine what kind of failure you're talking about? Okay, so this is going to be a very significant calculation. Okay, so after you have determined this one, just now you have determined the stress. Okay, I've done our calculation. We have found this what is the stress concentration factor, and we have calculated the actual stress. So now we have sigma T. Okay, now you have sigma T. So based on sigma T, now okay, there will be remember, for fatigue there will be sigma max and there will be sigma mean. So there is two value. Okay, so both must include Kf. Okay, you have calculated like just now, you calculated. Okay, so you have sigma max, sigma mean. Okay, that's why I put the word zero here. Zero here. Okay, zero means not yet not yet include Kf. Okay, so sigma max, sigma mean, you must include Kf for both, then you get the actual sigma max. So I put here sigma x 0, sigma mean 0. Okay, 0 means actually nominal. It's a term used by the book. Nominal, okay, maximum stress. Nominal, minimum stress. Okay, after you include Kf, then it become the actual sigma max and become the actual sigma mean. Okay, after you get this sigma mean and sigma max, what you do is use this equation, this one, to find sigma m, find sigma a. Okay, After you get sigma M, sigma A, you are ready to do the final part. This is the final part. Okay, this is the final part. Okay, so there are two ways to do this. One is to draw the chart. Okay, one is draw the chart. If you refer to the book Juvenile, they do not give you this equation. This equation is not given. Juvenile does not give this one. This one is taken from other books. The reason I include that inside here because if you have to draw the graph here, to draw the chart here, first of all, it takes so long time. Most probably you all take around 15 minutes. And then some more, because the chart is not accurately drawn, and your accuracy, of course, is very much even less. Okay, so your accuracy will be very, very low. And because of that, it is useless. So what happens is that I prefer you to use this equation. So how do you use this equation? If I ask you to determine, okay, using Goodman line, all you have to do is use this equation. Find sigma A first, just now, I've shown you. Find sigma M, I've shown you. You already calculated Sn, and you also know what SUT. So what you do is find this one. This will be the safety factor. Okay, so compare this safety factor with the safety factor proposed by the designer. Okay, the question say safety factor must be at least 2.0. Okay, so you check if NF is 2.0 or above, then you will say that the design is safe. If it's less than 2.0, then the design failed. Okay, so now this is what. Okay, so let me introduce to you this. This is the fatigue failure curve. Okay, now the first one is the Soderberg line. This is Soderberg line. Okay, now Soderberg line is not used by us. Only production people use it when they are doing forging, casting, right? Only them use Soderberg. So we will never use Soderberg. Okay, why is it we don't use it? It is too safe, too conservative. What means too safe? Means that it is the what the safety factor need to be high. Okay, and you do not want your design to be too high safety factor, right? Okay, uh, for casting and forging, it's okay. Okay, what we are going to use will be Gerber line, this Gerber line of Goodman line. Okay, now Gerber line is the one most popular, most used, one of the most used. Goodman line used to be the one used before, but now it's less used because it is a bit more conservative than Gerber. Okay, Goodman is more conservative than Gerber. But because Goodman line is always a straight line, whereas Gerber line is an ellipse, we will ask you to use Goodman line only. Easier to understand. Okay, and you can see the equation is one. This is the ellipse equation. This is ellipse equation. This is straight line equation. Okay, so all you have to do is find sigma A, find sigma M. You already know Sn, you know SUT. Find NF, you get your answer. Okay, understand? Okay, so what you have to do now is to finish up your assignment, homework, classwork. Okay, this one. Yeah, I want you to do part B. Calculate mean and alternating. Find the sigma M. Find the find sigma M and sigma A. Okay, take your piece of paper and start calculating. So you are thinking what to do now, what to do now. Find sigma max, find sigma min. Here you have actual 10 to 500. So what is the equation for, what is stress equation for tensile load? Tensile load is equal sigma AX is equal to 4F divided by
E.
pi d squared. Correct? Correct. Right? Did somebody say something? So what you do is, first of all, F is equal to 10. Find sigma AX. And then F is equal to 500. Find sigma AX again. So like I said, it's not so difficult. It's just that you have to do 2 times. After you determine, you determine sigma AX, you have to decide which one is mean, which one is max. Right? So one of them is sigma max. So one of them is sigma max, one is sigma min. Okay? So you have sigma max nominal, max nominal, 0 nominal is equal to what? Sigma minimum nominal is equal to, okay? So that one, okay? After you have calculated this one, then proceed to this one. What's the equation for tau? Tau is equal to what? 16t divided by pi d cube. Okay? So you have here 16 times 5 pi d cube. And the one is 16 times 14 pi d cube. Okay? So of course you know that this one is minimum because you know smaller. This one will be max. This one will be tau max. So have you got the answer? Max 0, because we have not included the stress concentration. So sigma max is equal to sigma max 0 time Kf. Sigma min is equal to sigma min 0 takkan rosak lagi. Hang again. Cannot use hot sheet. Hang. Let's proceed. Yes. Okay. So you have here sigma max sigma max is equal to sigma max 0 times Kf. What is Kf? What is value of Kf? Value of Kf just now we have calculated is it's gone. Never mind. I have that value. Kf is actually okay. Just now, if you have calculated, you know that Kf is equal to Kf for bending. So difficult this one. What is the solution? Okay. This is the solution. Okay. Always cannot disclose it. Okay. So here you have obviously just now you have just now 500. Okay. Okay. You have F500. Okay, this is 500 and this one is 10. It's very easy, okay, very easy for you to come to a conclusion that F max is 500, F min is 10. It's not, okay. D is equal to 8, correct? D is 8. Now T max is 14, it's so obvious. T min equal to 5 millimeter, okay. So based on this, material is 724, SY 414. So endurance limit Sn is equal to 0.5 CT62, S3 0.9. So you have Sn 223.948, basically 224 lah. Okay, 224 megapascal. Okay, 224 megapascal. Okay. Okay. So now to find KT, to find KF. Okay. So first of all, okay. Alright. Why this one? Oh yes. Okay. Why this one? Okay, let's try. So for to find KT, okay. Okay, to find KT, look for the diagram. Okay, this is the diagram. For the same one just now I show you. Okay. Alignment. It's okay. So based on this one, the one that is so much the same will be, I think, this one. Okay. Okay, will be this one. Remember, the 8. Okay, there's 3 of them. So which one you use? This one is bending. Okay, there is no bending. There's no bending, so cannot use bending. We have axial, we have twisting. So use these two. So you're going to use these two. Okay. So use these two. Okay. So that's what happened. We are going to use that too. Okay. Axial and also twisting. So use this equation again. So you have D to the 8, D to 12. What is D? D is the big one because this is the shoulder. For shoulder, there always be a big one and the small one. Okay. Okay. So this is D, small d, this is big D. Okay. The big D is this one. Big D is 12. Small d is 8. Now what is R? RF is the fillet radius. Fillet radius. So this is fillet radius too. So what you need to do is find R divided by D. R divided by D. So R divided by D is 0.25. And then you need one more, D divided by D. Yeah, D divided by D. Okay. So D divided by D is 1.5. So all you have to do is look into this 0.25. This is 0.25. Okay, I already marked it here. Okay, this is 0.25. And then DD is 1.5. So 1.5 is 1, so is here. Right? So 1.5 is this line. This line. So go here, stretch. So you have 1.47. This is 1.47 here. And then look into this one now. Okay, we have this one that the value is the same. This one RD is still 0.25. Okay, and then the what is DD is 1.5. So you will have to make some assumption here. Okay, okay, try to do interpolation. What is mental interpolation? You get the value here, right? This one value here. Okay, and then proceed, you get 1.16. Okay, so for this one I put as KTS. Okay, for top I use KTS. For axial or bending I normally use KT. If there are both axial and also bending, then I use KT1 and KT2. Okay, right now there is only one axial, so I use KT and I use KTS. Okay, so after that, after you have KTS, okay, find the SUT 724 drawn steel. Okay, for that value you can get Q. So here you have two value. Remember I mentioned to you that you have two value here. This one is for bending and axial. This one is for torsion. Okay, so you have to use two of them. Okay, so now you have the value as 74, which is 105 kpsi. 105, this one, so 105, this one, and then R2, where is R2? Okay, R is equal to 2 millimeter. Where is R equal to 2 millimeter? Here, R is a 2 millimeter. Okay, so you have 105. Okay, this is 50, 60, 80, 100. This is one. So 105 is slightly higher than this one. So it's somewhere a bit higher here. Okay, so here. Okay, so here you go 0.82. The next one is also 105, but 105 now is higher, 80, 120, 100. So it should be around here. Okay, around here. So the value now is different. So it goes to okay, the value now become 0.85. Okay, remember there are two of them. So you have 0.82 and 0.85. Okay, so after you have Q, find KF. So you have KF, KFS. This is for torsion. So you have already calculated. So this is for actual stress. So you get this one value. This max, minimum. This is tau max, tau min. Okay. So what you do now is find sigma M, find sigma A. This equation is standard. Don't forget and don't get mixed up. Okay. Don't say sigma M is sigma max minus sigma min. Okay. Remember sigma M is plus. Sigma M is plus. Sigma A is minus. Tau M is also the same. Use the same equation. Okay. So you get sigma M, you get sigma A, tau M, tau A. Okay. After you get tau M, tau A, now this equation, you can find it here. Okay. Here. What page is this? Table 8.2. Okay. Okay. You can see here. Okay. Just now, you have already calculated sigma A. You have already calculated sigma A, tau A. So how to combine them? Okay, you combine them. This is E for equivalent. So sigma E alternating. Just now sigma A, tau A. So sigma A this one. So use this equation to find sigma EA. And then use this one is equivalent mean. This one equivalent mean. So use this equation to find equivalent mean. Okay. So after you get this one, then apply them into this equation, into this. Okay. After you have done that, then apply them into the failure. What is it? Apply them into the failure criterion. Okay. Where's the note? Static slide. Okay. So you get this one, sigma EM, you get sigma EA. Okay. Then test for fatigue. This is equation. Okay. So you have SUT, SN is already calculated, SC is calculated. So sigma EA is calculated. So Langer yield line is 2.078 and F is equal 1.826. Okay. So now let me explain you what is Langer and what is, because just now I didn't explain fully. But this slide. Okay. Okay, so let me erase this one first. No simpler way. Okay, okay. Now, this is the fatigue failure criterion. Goodman is fatigue failure criterion. Goodman is a fatigue failure criterion. Gerber is also fatigue failure criterion. Soderbergh is also fatigue failure criterion. But this one is mostly used for those who do forging and casting. Okay, Soderbergh is for forging and casting. Okay, Gerber is quite popular now, but for our class, we are going to use Goodman line. This one is the fatigue failure criterion. So what is Langer yield line? Okay, Langer yield line test for first cycle failure. Remember not when I show you the Moore specimen? Okay, when I show you a Moore specimen, when the load is 166 pound force, right? The first cycle, okay, the motor just started, the specimen broke, right? So the specimen broke at the first cycle. Okay, so that is what Langer is all about. Langer is to determine whether the specimen will fail at the first cycle or not. Okay, Langer will test whether the specimen will fail at the first cycle. So like just now, so if I put it 166, then Langer will show that you will fail. Okay, so what happen if Langer fail at the first cycle? If if you have calculated and you discover that Langer failed already, there is no need to do any more analysis, because why? First cycle already broke, so there is no more, the specimen is gone already. Okay, so no need to do any more analysis. But if Langer is okay, then you have to proceed and use one of these. Okay, so of course in this class, after if Langer is okay, then you must use Goodman line. Okay, so this is Langer. This is Goodman line. You have already calculated just now. You have calculated. So all you need to do is this one will be sigma EA. So Langer NY will be equal to SY. Remember, SY. Okay, based on the calculation now, it will be sigma EA. Remember, got A there, equivalent, plus sigma EM. Okay, and then some more, you will have for Goodman. Okay, determine this one. If the value is okay, or what is it okay? The question tell you safety factor, what is which is okay. Okay, so if safety factor say is 1.5, so if the value is more than 1.5, that means okay. So if that is okay, what you have to do is proceed your calculation. However, if it fail, okay, at the first cycle, in other words, we just apply the load before you manage to do anything, the specimen actually broke already. Okay, so that is what it's all about. Okay, so NY, this for Langer, NY calculate. Okay, so after that, when this one is okay, this one is okay, then you go for Goodman line. So what happened? Goodman line will be sigma EA over SN plus sigma EM over SUT equal to 1 over NF. To find NF, okay, you know sigma EA, you know sigma EM, you know SN, you already know SUT. So find NF. If NF is higher than specified, then it is a pass. What happens if it doesn't pass? Means that it will fail. Okay, it will fail. What does the fail means? Fail means that it failed to have permanent life. It failed to have infinite life. Okay? Okay. It does not mean that it failed totally. Maybe it won't last forever, but maybe it will last like 1 hour, 2 hour, depending on the RPM. Okay, so it may last how many cycle? Maybe like 900,000 cycle, maybe last 500,000 cycle, maybe last only 10 cycle. Whatever is it. If safety factor is less, so right now we assume safety factor 1. So safety factor is 1. So if it's less than 1, then we know that what is the specimen do not have infinite life. Okay, specimen do not have infinite life. If safety factor is greater than 1, then the specimen have infinite life. So if this safety factor is higher than 1, we got infinite life. So calculation finish. You just say that the specimen will last forever or something like that. Okay. What happened if the specimen fail? Okay. Just now we test, it doesn't fail langer, so it does not fail at the first cycle. But obviously, it failed a few thousand cycle, maybe 1,000, maybe 5,000, maybe 10,000. So because of that, you now have to find out how many thousand cycle. That one will be in the next class. Okay, so any questions? Or you all burnt out already? Are you all still there?
Doctor.
Yes. Sure. Okay, so you know the procedure how to calculate. So what I want you to do is to finish up the calculation. Okay, finish up the calculation. Can you submit today's? Can you submit tomorrow? This one, I've given you most of the solution. I want you to finish it and then submit to me tomorrow before night. I'll put the question in the portal. You submit through the portal. Okay.
Okay,
So
doctor.
come a revision before you all forget. If you need some guidance, okay, actually we can arrange a class also tomorrow. Okay, I can stand by. I can stand by if you want. Just tell me what time you want. Okay, stand by. So those of you who try and then still cannot do it, okay, you can ask me. Okay, what time will it be? Is 9:30 okay tomorrow? It's not compulsory. I'll be around at 9:30. Please, somebody remind me. Okay, I'm a very busy man. I might forget about you all. So, okay, so if you want tomorrow at 9:30, I'll stand by. Open up the this Google Meet. So those of you who want to ask question, you can do it. Okay, tomorrow 9:30. Somebody will have to remind me. Okay. Although I try to remember, but just in case. Okay. So anyway, you have to finish it before night time tomorrow. Any questions?
No, doctor.
No question? So the subject easy. You know, your senior told me, sir, he said, this subject is the toughest subject in all the courses. Okay? This is the most difficult subject in all the courses. Okay? And then one person adds some more. And this topic is the most difficult topic in this subject. So welcome. You are now going through the most difficult topic in your engineering life. Okay? So try, okay, try. It's not difficult, but you must do a few exercises. Remember, it's very important. If you want to do design later, or you have to do a calculation later, you have to go through all this. Okay? Of course, there will be senior to help you, but It's good if you don't have to rely on them, okay, and do it on your own. Okay, so if you are okay, we can close. Okay, we can quit. What you call it? Break. We can break, and then if you want tomorrow 9:30, okay, I will open up a Google Meet. So those who want to join can join. It's not compulsory. Okay. If you have any question, you can ask tomorrow. Okay.
Okay, Doctor.
Okay. Lemah je semua ni tengok. Okay. You all sound very weak already. Okay. No, I'm sorry. So because we missed the last class, that's why I compress everything into this class. Otherwise, I break it into two. Okay. We have no choice. Okay. So I compress. I know some of you still tired, but never mind. It is for good cause. So thank you very much. If there is anything else, okay, we will quit. Thank you. Goodbye. Assalamualaikum.
Thank you, Doktor.
Terima kasih,
Thank you, Doctor.